I'm John Lyles, a caver and a cave owner in New Mexico. This is Edgewood Caverns in Santa Fe County in the southern end of the county, about 30 minutes east of Albuquerque, very close to Interstate 40. I'm going to talk about the CO2 issues in this cave. But the cave is a densely jointed cave in Edgewood. It contains a single 38-meter deep entrance shaft that was drilled and cased with a half-meter diameter steel pipe. That's about 19.5-inch ID. To give you an idea, it's a pretty interesting entrance. It was drilled and cased in 1970. It's a dry cave in the Pennsylvania limestone in the region with a solution in large joints going every direction, mostly east, west, north, south predominantly, and it's in the Madera Formation. It's been mapped to almost 8.3 kilometers, about 5.2 miles as of last year, and it has barometric driven winds at the entrance. It only has a single entrance. A detailed talk of the history of the cave was given at the conservation session at the 2018 convention. Here's the cave building I had built over the entrance on the concrete pad there, and a little building I built last year for changing clothes and putting batteries in your lights, just a little more space for people so they're not all crammed in that one little building around the entrance getting ready to go in the cave. You can see the air coming out of the entrance shaft here. This is a map of the cave by Garrett Jorgensen, and in the profile you can see the single entrance shaft going down. The cave's roughly 150 feet under the land, and the deepest parts of the cave are in the far east and the west. You can see them there, and in the west it's the northwest corner where the biggest new passage has been found. That was all explored in years ago and scooped, but never surveyed, and it was lost. And Garrett refound it, and so it turns out that's where a lot of CO2 is coming from, those deep areas in the cave. I'll talk about that now. The Estancia Basin in New Mexico, where Edgewood is located, is geologically known to source CO2. It's found in local water wells, it's found in this cave, and there's actually production wells in the region that have operated to make dry ice years ago. There's levels as high as 20,000 parts per million. That's a 2% CO2 in the deepest cave passages of this cave during low pressure weather events, such as when the barometer goes low during a thunderstorm, stormy weather. The cave starts exhaling, and the exhaled air has a lot of CO2 in it coming from deep. CO2 is heavier than air normally, so it would accumulate down at the bottom of the entrance shaft, and of course you can measure it down there, and it accumulates in the deepest parts of the cave. But it does move on out of the cave as well because of the cave blowing. So the best time to be in this cave is when there's a high pressure and the cave is inhaling fresh air through the entrance. The National Institute of Occupational Safety Hygienist, I believe that is, has a recommended exposure limit of 5,000 parts per million, averaged over a 10-hour work shift. That's 0.5%. And 30,000, which is 3%, not to be exceeded during any 15-minute work period. So 3% is really bad. 4% it gets to a point where you may pass out. 5% there's pretty good chance of death. So you don't want to be in the cave when it's 3%, and even 2% is pretty bad. We have experienced it, and it depends on the person on what kind of effects you'll have, but we prefer not to be in there if there's a 2% reading in the low points of the cave. The American Council of Government Industrial Hygienists has similar levels, and they have an 8-hour work shift at 0.5% and a short-term exposure that's also 3%. So like I said, now that I own the entrance to the cave, I needed to develop a system that's using a commercial CO2 sensor that will be placed in the cave soon. Additionally, portable gas monitors will be used by all the cavers who are going to be in the cave. The first instruments I got were some on eBay, and they're Telair 7001s. These come under various names: General Electric, Honeywell. Various companies put their name on them, but it's a Telair design with their sensor, and they're really made for air quality in buildings. And it turns out they max out at about a 0.5%, although they'll read almost to 1%. And so I started out with this naively thinking the cave's not going to be that high. And here I have a Hobo 4-channel data logger attached to one, and I'm reading the analog signal as it goes down this bucket into the cave, so I could map the CO2 levels as it drops. And I also added a mechanically operated ridge vent to the top of the building after the building was built, because it was just accumulating in that building and it was really bad. In addition, there was a lot of moisture in the building, causing a lot of sweat and rust on the iron structures, so the steel beams in there. So now the roof vent stays open all the time, so there's some air movement. And the cave has a lid on it, but there's some leaks, so it does breathe around that. But when we're in the cave, we open the lid entirely, and the air comes out and goes through the roof vent. Here's the reading I got when I lowered the bucket. It's the black line, and you can see me lowering it, and it was reading. It got higher and higher. It got up to 750 to 800 parts per million, which is really small, but that's just, 400 to 500 is normal atmospheric CO2 level outside. And you can see it went up as it was lowered, and the cave was inhaling. So this is actually showing that there is some CO2 buildup, even though it's bringing in fresh air. And then I opened the ridge vent at the top, and you can see it dropped again. So it dropped at about 50 parts per million just by doing that. And over time, it actually dropped quite a bit more. It took a little while. It took about 8 minutes, 6 minutes, and then it dropped down to a much safer level. So having that vent open with the entrance open is a good thing. The Telair meters were useless for safety, however, because once I got into a region where it was about 1%, the meter read 9999, and you can see it on the right. So I don't know if it was 1% or 1.5% or what, until I got some different instrumentation. There are many different OEMs that make these instruments, and they make the sensors as well as complete instruments. They all use, they're used for breweries, chemical plants, greenhouses, anywhere, dry ice areas, anywhere that CO2 could build up and cause a human safety hazard in low areas. All of them use a non-dispersive infrared technology in the sensor, and that's described in the references, so I'm not going to get into that here, but it's a pretty common technique, and it's really interesting how it works. The older types used incandescent lamps with filters. So of course they burned out over time, they used more power, and so if you're buying something, be sure to look for infrared LEDs in it, because it'll drop the power consumption quite a bit on the sensor. They have dual beam and single beam designs, and there are advantages for both. You just have to read up on it, but I think both of them work pretty well. And there are some advantages in the calibration and long-term stability of one versus the other. And some of the portable meters, one of mine actually has an electric pump in it. So you can put a hose on it and you can sample ahead of you with a probe. Those are really good in industrial settings, but they also work faster even in the cave, but they use more power. Others just use diffusion through a little membrane that keeps moisture out and allows it to go in. And that's typically what's used in the permanent systems that don't use much power. And all of them have a small warm-up time around a half to 1 minute before they have a stable reading. Calibration. This should be done regularly if you're using CO2 instrumentation for human safety, because what if the instrument is way out of calibration and you're believing it? You don't want to die over this. So you should get some 17-liter calibration cylinders. Those are about the size of a small propane torch that you use at home, and a little regulator that goes on those. And you can get a 0 and then a level like 3 or 5% CO2 and nitrogen. 0 is usually pure nitrogen, so it's just a cylinder of nitrogen with no other impurities. And do not skip calibration on these instruments. You can do it at your intervals that you prefer. Most industries will do it every 6 months to a year. Some people have a setup where they bump test the instrument before they actually use it every time they use it, and that's very common. The bump testers are even smaller. They're just little tiny cylinders, but they don't last as long. At Edgewood, this will require a person in the cave at the sensor and a person on the surface to switch the system into calibrate mode while the person in the cave connects the regulated source of gas to the inlet of the sensor and gets a stable reading. These gas standards are available online, but you have to have a business address, and you can also pick them up at Granger. Day-to-day use, you can depend on typical values and see that the instrument's working. You'll see it fluctuate, and I hope to gain some confidence that the system's working by seeing the peak excursions over different weather events and knowing that, yes, it is still working. Portable meters can be quickly checked outdoors because, like I said earlier, 400 to 600 parts per million is the background value depending on if you're out in the open or in a city or something. And if you just breathe on it, you'll see it jump up quickly to over 1,000. Here's an ISI on the left. It's about 8 years old, 10 years old that I rebuilt. I got it on eBay. It has a pump in it, and the batteries were shot. It had nickel cadmium. I converted it to lithium ions now. And then the one on the right is an analox that's actually made for putting in submarines. Submarine people use this. And it's a very accurate unit. It has CO2 and oxygen, so it's a dual gas sensor. And those are the two that can fit in a small box and go in the cave on caving trips. Here's a highly accurate analog sensor made in the UK that reads up to 100%. That's unfortunate because I wanted one that read up to 5%. I got this thing cheap on eBay, and it won't work because it won't have much resolution at 1 to 3%, which are the levels I need for human safety. It runs with a 4 to 20 milliamp current loop output, so it goes into an analog system as far as readback. This is the system that I'm going to install. It's made for breweries and places like that, but it only has a top end of 5%, but that's plenty good enough for Edgewood. And it uses a Cat5 cable to a remote unit that mimics what the unit downstairs would be reading. They're digital communications, so there's no 4 to 20 milliamp. And this unit, unfortunately, is not really made for the environment of caving with the humidity, so I've got to put it inside of a tight box, like a NEMA box with a certain standard of moisture integrity, and then use a diffusion membrane for the CO2 to waft into the sensor. I have to do that work before I can put this in the cave, put it in a little bit bigger box, oversized, and seal all the connections. This is the gateway that connects the readings to the internet or to the cloud, and this device here reads 4 to 20 milliamps, so it would work best with an analog system. And the LTE is basically, there's a SIM card like you would have in your phone, and I have an account set up with local LTE through Verizon, and it's about $4 to $5 a month, and that gives you a limited amount of data. That's just data. You can't have voice on it, and you can make it work off a time clock and turn on and off and regularly read readings, or you can remotely turn it up and you can have it read the readings. So the beauty of this idea is that I can actually read it. I live 70 miles from the cave, so I can read it from home and know if is the cave worth even going into. And otherwise, it's too high a level, we're not going today, or if the weather's looking like it's changing. Here's a couple of other ones. These are more digital. These would actually have like serial I/O, one analog, and like an Ethernet input, and they connect to LT as well. So you can buy these types. Getting cables down to the sensor will be fairly easy because of this abandoned water well that originally pierced the cave back in the late 60s. It's a dry water well, and it goes right in through and crosses the cave passage, only less than 10 feet from where the big steel-cased entrance shaft hits the cave. And this was plugged up, so I remove the concrete plug from it and excavate it around it. And down in the cave you can see where I cut it with a portable grinding cutoff tool, so I could actually remove that steel cover and bring the cables through. It continues on down deeper than this. It's a dry well, and all I'm going to do is run cables down it. And then on the surface I plan to take some PVC pipe with elbows and make a U-shaped elbow so that I can bring the cables up and not have debris and water going down in the cave. And then I'm going to heat that up and not shrink it, but heat it up with a hot air gun and shove it into this pipe so it'll fit tightly. And then I can put a cap on it so that it doesn't breathe a lot if I want to keep the air flow controlled and only have it going through the building. So this will enable me to bring power down to the sensor system as well as the signal back up to the LTE gateway. For power, I have a 25-watt solar panel mounted on the building now, and that's also where the LTE data and IoT antenna will be mounted on the top of that little pole. I have a regulator that I had left over from some old project that was no good. The solar panel had died. That's just about the right size to run with that 12 amp hour SLA battery there. So that battery's topped up all the time, and there's plenty of sunlight because this is out in the middle of flat ground with not any trees on the south. So Edgewood gets a lot of sunshine, so it stays topped up. So that's the end of my talk. You can see what I've been working on. It's been about a year's work on paper and trying out different hardware, and now my hope is to get it down in the cave as soon as I can get a team in there without worrying so much about COVID. I don't know when that'll be, but here we all are going in the cave, happy-go-lucky. A year ago we didn't have any idea that something like COVID would come along, and this is a typical team going down to survey in the cave in the new area. With that, here are the references I was talking about. I hope you've enjoyed this, and thanks for listening.